We start to introduce our work on geometric cover with outliers. The problem we study is a generalization of a classic problem, which is geometric cover. It is formulated as covering n given planar points with a least number of unit squares or unit disk. Here the unit squares are those ones whose side length is 1, and the unit disk are the disk whose radius is 1. So no matter we use unit squares or unit disks to cover, the problem is strongly NP-hard. That means there's no polynomial approximation whose time complexity doesn't depend on the approximation ratio. For the unit disk cover, we'll also consider a restrictive version. So in the restrictive means that the disk centers can only be in the input point set, and the restrictive problem is still NP-hard. So we notice that in the covering problem, the outliers can dramatically affect the numbers of unit squares or unit disk. For example, in the right figure, we have actually 1, 2, 3. We have 3 outlying points, and each of them require an additional unit disk to cover. So you can see that if these 3 outliers actually double the number of unit disks to cover the whole point set. So to deal with such cases, we hope to design an algorithm that can detect the outliers and cover the remaining points with the least number of unit squares or disks. The formal definition is as follows. We hope to cover all except T of the points with the least number of unit squares or unit disks. And we use n to denote the number of input points, and T and the T excluded points are usually regarded as outliers. And we also consider the problem when the disk centers are restricted to be in a given point set. An important method to solve the classic unit disk or square cover problem is called shifting strategy. The method requires dividing the plane into vertical strips. Each of them is of width W. The width of each, we group every L consecutive strips into a wide one. And here, let's take L equals to 5, for example. We can actually group -4 to 0, group them together into a wide strip, and 1 to 5, group this together. Or we can actually group -3 to 1, this 5, and 2 to 6, the next 5. And in general, there are L ways to group L consecutive strips whose width is L times W. For each grouping, actually there are almost non-empty white strips, as there are just n input points, right? And for convenience, we will call the original strip a thin strip, and the grouped strip a wide strip. So how do we get a global solution from such a dividing? Actually, for grouping, we can apply a local exact algorithm A on each wide strip, and then combine. For example, for this example, when L equals to 3, we apply A here to get a local optimal solution, and A here to get another, and A here to get and then we can combine all the local optimal solution together to get a global one. Well, the global solution we develop this way is actually an approximation to the global optimal. So now we show how to prove its approximation ratio. we first notice that a unit square can actually intersect at most this number, the CU of 1 by W plus L, such number of different white strip. Again, we take an example. We have a look at the example. So when W equals to 1 by 2 and L equals to 2, here the unit square here, it actually intersects 4 white strip. The first one is -4 to -3. The second is -3 and -2. And the third is -2 to -1. And the last is -1 to 0. 1, 2, 3, 4. It intersects 4 white strip from different grouping. And we let SOL denote the solution for the ice grouping, and OPT denote the optimal solution. And we let OPTIJ denote the restriction, denote somehow the restriction of OPT onto the J's non-empty white strip in the ice grouping. So it is a set of unit disks in the optimal solution that intersect the J's non-empty white strip. As we can see that OPT, such a restriction must be a solution to the J's non-empty white strip, right? It is a local solution. So by the optimality of if we apply A onto Xij, we will get a local optimal solution, right? So the solution we get this way, the size of the solution we get this way must be no less than the size of the local optimal. So we have this inequality, and by the definition of the SOLI, which is a solution of the ice grouping, it is a union of all local optimal solution of all white strip. So we have this. So this equation is actually by definition, and we apply the inequality here. We sum the both sides of this equation over I and J, and we get this one. And again, when as we just mentioned, a unit square in OPT can intersect at most such number different white strips, right? So we have this inequality, and we then combine this inequality to get this one. So this means that the size of all the solutions for different grouping is no larger than such number times the size of the optimal. And then we choose the minimum among all the solutions for different grouping, and we have this inequality. And it is for the unit disk cover, it is the same. We can while the approximation ratio is different, we can get this one. So the question is that shifting strategy doesn't consider the outliers. When there are outliers, how can we develop such a strategy? The challenge is to determine how many outliers on each white strip. We need to somehow guess the numbers on each. We need to determine the number of outliers on each strip before we apply the shifting strategy. So actually, there is a brutal way to do that. We can for convenience, we let Xij to denote the points on the J's non-empty white strip in the ice grouping, and Tij denote the number of outliers in Xij. So we can try all the combinations, which is a union from J to N. Remember that there's most N non-empty white strip and a group in a grouping. All such local solutions for different Ti1 to Tin only subject to their summation equals to T. So we just guess all the outlier distribution over different white strip. This will cost too much time, right? Although it works, but it costs too much time. And we just we actually have a smarter way to do that. Our method is still by guessing, but it is in a smarter way. So we guess all the numbers of power 2, which is smaller than t, together with 0 and t. We try all such Tij, and then apply a local exact algorithm to get the local optimal solution, OPTXij Tij. So on Xij, we define the Fij to be the lower convex hull of all Tij and the local optimal solution. For all such points, we find the their lower convex hull, and then we define the capital Fi to be the summation of all the lower convex hull. So you can see that each of the convex hull is defined for a single white strip and a grouping, and we just sum them together. And we define the solution SOLI to be the minimum point of Fi. Because each Fi is a lower convex hull, right? We can so Fi is also convex. We can find the minimum point of Fi, and subject to the summation of the outlier is no more than 2t. And we give an algorithm in the paper that the minimum point can be found in nt log n time. Actually we can prove the approximation ratio. So we let Tij star denote the number of outliers in each white strip in the optimal solution OPT, and Tij prime denote the power 2 between Tij star and 2 times Tij star. So the solution we get for the ice grouping is the size of which is actually the minimum value of Fi, right? And because it is defined to be because SOLI is defined to be the minimum point, and we have the minimum value. So the minimum value is no more than the value at Ti1 prime to Tin prime. And remember that for each power of 2, we get a solution OPTXij Tij, right? So we have this equation here, and this equation and this inequality here. And because OPT Xij Tij is decreasing on the number of outliers, so that means when there are more outliers, the number of unit squares or unit Ds to cover the point side will be smaller. So we have this inequality. And again, unit square disk in OPT can cross at most such number different strips of white strips in all groupings. So we have this one, and further this for unit square cover. So such inequality actually enables us to focus on the finding local solutions of unit disk or square cover. So we can actually use the dynamic for so we focus on the local solutions on a strip. We can use dynamic programming to design local solution. So both for square and disk cover. For example, we consider the unit square cover for the points lying in a vertical strip whose width is 1, and the number of outliers to be detected is 2. So as shown in the right figure, the points of the first square, it actually can be here or here. For such a cases, it doesn't exclude any points. It doesn't exclude any points from the first square selection. And after we choose the first square, there can be at most t points between the second and the first, right? So the second square can be here or here, or actually it can be also here. So in such a way, we can derive the recursive formula of the dynamic programming. So as you can see here, we use an NIK to store the minimum number of unit squares that cover at least I minus k points from x1 to xi. X1 denote the lowest points, and xn denote the highest, and x1 to xi is order in the increasing order of their y coordinates. So if we are going to cover I minus k points from x1 to xn, then as like this example, we can either choose that the first square can cover we can choose the first square to cover xi, and then so if the square covers ci points, then the next point to cover the index of the next point to cover is I minus ci, right? So we have we have NIK, it can be such a value, right? Or we can if we do not cover xi, we regard xi as an outlier, then we have then NIK can be such a value. So that means that the unit square can be selected this way to exclude xi, or can select such a position to exclude xi and xi minus 1. For the unit disk cover, on a strip, we can also develop a dynamic programming. Well, the dynamic programming is upon the top spanning set instead of the unit disk. Here, the top spanning set is defined to be a set. We say a set of unit disks to be top spanning. So if the other unit disks except the other unit disk is at the highest, covers points above the highest disk. So that means in such a set, a unit disk is either the highest or it covers a point above the highest disk. And we actually can prove that for when the width of the strip is no more than 4 by 5, there exists an optimal solution that contains no top spanning sets of more than 2 disks. So we can then apply dynamic programming over all top spanning sets whose size is 1 or just 2. And for the restricted version, we'll have a similar conclusion here. And our results is so together with a shifting strategy, we first introduce the local algorithm, which is the dynamic programming for unit disk and unit squares on a strip. We are able to give 3 by criteria approximation algorithm. The conclusion can be found in the paper. Okay, thank you.